Okay, good afternoon everyone. I am Shivani Thok and today we'll be doing the tutorial for second week content of the course Principles of Signals and Systems. And in this week, I hope you all are able to see my screen. So in this week, the content covered was related to classification of systems and properties of LTI systems, and few examples were taken based on classification of signals and classification of systems. For classification of signals, a lot of examples were covered in the previous tutorial. So in this tutorial, I'll majorly focus on classification of systems and properties of LTI system. Okay, so first let us have a small recap of whatever was covered in the second week. So for system classification, the first system classification that was covered was actually based on memory and causality, which was covered in the previous lecture. But let us first revise that also. So the first one was memory based. So a system was known as memory based if output of that system depended only on the current instant. That is, if this depends only on current instant input or current input, that is x of t, then it is a memoryless system, else it is a memory based system. So this was the first thing that was covered, and the second thing was causality. Causal systems. So if the output y of t, or let's say y of n for a discrete time, if this depends on current input or past inputs, then such systems are known as causal systems, else those are known as non-causal systems. So these two classifications were covered in previous week. We'll see some examples of these also in this tutorial, and we'll see more on classification of systems. So in this week, the first classification that was covered was linear systems. And for a system to be linear, it should satisfy these two properties. So a linear system should satisfy additivity. So what does this additivity means? So if I have an input x1 of t, and this gives me output as y1 of t, and if x2 of t, I have an input, and if it gives output, if the system t gives output as y2 of t, then if I give input as addition of these two, that is x1 of t plus x2 of t, then the output of the system should be equal to sum of the output that was due to x1 of t and that was due to y2 of t. So if this property is satisfied, then the system is known as additive. Kindly please unmute yourself. The second property that a linear system satisfies is homogeneity. So what does this say? It says that if for input xt of t, my output of system t is y of t. So if I give a scaled version of this input, then the output should be scaled version of the output due to x of t, and this scaling constant should be same. Like if I scale the input by 2, my output should also be scaled by 2. It shouldn't be some different constant, it should be the same constant. So if this satisfies, then the system is homogeneous, and if a system is additive and homogeneous, then such a system is known as a linear system. The next type of system that was covered was time invariant system. So this says that if I shift an input by some t naught factor, then my output will also get shifted by same constant, same time interval t naught. That is, t of x of t minus t naught should be equal to y of t minus t naught if y of t was output for x of t. And if this situation happens, then the system is known as time invariant. Otherwise, it is a time varying system. And next thing that was covered was stability. So for stability, the criteria that was used was bounded input, bounded output stability. So this is also known as Weibo stability. So what does this mean? If my input is bounded by some constant, let's say c, if my input is bounded by some constant c which is less than infinity, then if for all such possible inputs, if my output is also bounded by some other constant, let's say c prime, then for every bounded input, if I am getting a bounded output, then the system is known as Weibo stable system. The next classification that was covered was feedback systems. So in feedback systems, and the output after some processing is again fed back to input. So in such systems, the output is also a part of the input of the system. The major classification that was taken was linear and time invariant systems. So if a system is linear as well as time invariant, then such systems are known as linear and time invariant systems, and or in other words, in short, they are known as LTI systems. And a very special property of this linear and time invariant system is its impulse response completely characterizes its LTI system. That is, we can obtain the output of this LTI system if I am given the impulse response. So what is an impulse response? If I am having a system, let's say t, and if I give a unit impulse delta t as an input, so the output will be h of t, and this is known as impulse response. And for output of an LTI system, the output of an LTI system is given by this convolution integral, which is given as this y of t is equal to integration from minus infinity to infinity x of tau h of t minus tau d tau. So this is the convolution integral. That is, for any input, I can completely obtain the output using only impulse response. That's why an impulse response completely characterizes the LTI system. After that, certain properties of convolution were analyzed. So the first one was commutativity, and it said that if x of t is convolved with h of t, this sign here, that is asterisk mark, is basically a symbol for convolution. So this is equal to h of t convolved with x of t. The next property that was taken was associativity property. So it said that if I convolve h of t with h1 of t, and this again is then convolved with some second system, that is h2 of t, then this will be exactly equal to x of t being convolved with convolution of h1 of t and h2 of t. So this is associativity property, and the next property that was considered was distributive property. So if I convolve x of t with addition of h1 of t and h2 of t, then this is equal to x of t convolved with h1 of t plus x of t convolved with h2 of t. So these are the three properties of convolution, and then graphical representation of convolution operation was discussed. So it is actually consisting of four parts. First one is flip, that is if I am having an impulse response, let's say it is h of t is equal to e power minus t ut, then first I need to flip this. So this is actually my h of t, and let us consider this variable as h of tau, because if we look at this integral, it is a function of tau. So let us say that it is h of tau. First thing that we need to do is flip it, that is first find what is minus h of minus tau, then we need to shift it something like this, shift it by a unit t, something like this, and then what we are getting here is h of t minus tau, and after getting this we need to multiply it with x of tau and add or integrate it. So basically this is integrate, not multiply. Add or integrate, and we need to do that for all values of t. So these four operations characterize the convolution operation entirely. We'll understand this better with the help of examples which we'll solve today. After that, some properties of LTI systems were discussed. So like how the impulse response and other things will be there. So first thing that was discussed was memoryless system. So it was said that if my system is memoryless, that is if input output relation is something like this, then its impulse response is simply a unit impulse which is scaled by a. So this is its impulse response. For causality, non-causality and anti-causal systems, so a system is causal if its impulse response is 0 for all t which are less than 0. It is non-causal if there exists some t less than 0 for which h of t is not equal to 0. Like for some t which is less than 0, it is having a non-zero impulse response. And the third one is anti-causal, and for this h of t is equal to 0 for all t which are greater than 0. The third thing that was discussed was Bibo stability. And for Bibo stability, it was said that if h of t is impulse response of an LTI system, then the system is Bibo stable if this impulse response is absolutely integrable. That is, integration of mod of h of t over all possible values of t is less than infinity, then the system is stable. And after that, the eigenfunctions and transforms were also discussed, and I'll discuss this using an example which we'll solve afterwards. So now let us look at some examples. If you have any doubt till this point, please let me know. Okay. So let us look at the first question that we are going to look today. So the first one is classify the following systems based on memory, causality, linearity, time invariance and stability. And the first example is y of t equal to x of t plus x of t minus 6. So this is the first example that we need to look at. So let us first look at memory. So if we observe here, we are having a term x of t minus 6. This term indicates past dependency. and this term is current input. Since we are having a past dependency, it is not a memoryless system. So this is not memoryless. But if you observe, the output is depending only on the current and the past input, which means that it is causal. Since there is only a past dependency, it is causal. Now let us look at linearity. So for linearity, we need to look at two properties. The first one is additivity and the second one is homogeneity. So first let us look at additivity. So we'll look at additivity. And for additivity, suppose for x1 of t, if my input is x1 of t, then output of the system, let's say, is y1 of t. Similarly, for x2 of t, let's say the output of the system is y2 of t. Now let us consider the input x1 of t and y1 of t. But before that, what will be the value of y1 of t? It will be x1 of t plus x1 of t minus 6. Similarly, y2 of t will be x2 of t plus x2 of t minus 6. So what will be the output of x1 of t plus x2 of t? So this will be x1 of t plus x1 of t minus 6, or let's say x1 of t plus x2 of t, that will be corresponding to this part, plus x1 of t minus 6 plus x2 of t minus 6, which will be corresponding to this part here, which means that this is equal to y1 of t plus y2 of t, which is equal to the sum of individual outputs, and that's why the system is additive. The second part for additivity is homogeneity. So we know that for x of t input, the output is xt plus x of t minus 6. So let us see what will be the output of c times x of t. So that will be equal to c of x of t plus c of x of t minus 6, which is equal to c times x of t plus x of t minus 6, which is equal to c times c times y of t, which means that the system is homogeneous. So therefore, since the system is homogeneous as well as it is additive, these both things imply that this system is linear. Okay. So the next thing that we need to check is time invariance. So the fourth thing that we need to look at is time invariance. And we know that the output for x of t, which is equal to y of t, is given as x of t plus x of t minus 6. So now let us first shift the input. So let us see what is the output of x of t minus t naught. So what does this mean? this means that we are just shifting this input, like this t naught has to be added in this argument of input, that is it will be x of t minus t naught plus x of t minus 6. This was the argument of x of t, and in this we need to subtract this t naught. So this means that we are shifting the input. Like if I am having input as x of 2t, then shifting this input by t naught will imply that x of 2t minus t naught. This will mean shifting of input, and we don't have to replace t by t minus t naught. So this point has to be taken care of. And now if we shift the output, that is y of t minus t naught, now in this case we need to replace every t using t minus t naught in this equation. So that will give me as x of t minus t naught plus x of t minus t naught minus 6. So if we compare these two, these are equal. So shifted input leads to shifted output, and the amount of shift is also same, and that's why this system is time invariant. Let us look at the fifth property that we need to look at, and that is stability. For stability, our definition is we need to check for all bounded input if our output is bounded or not. So let us assume that my input is bounded by some factor b of x, which is less than infinity. Now let us look at what does this mod of y of t look like. So this is equal to mod of x of t plus x of t minus 6, which will be less than or equal to mod of x of t plus mod of x of t minus 6. So here I am using triangular inequality. And again using this bound, which is in equation 1, we can write this as less than or equal to bx plus bx, which is equal to 2bx. And we know that since this bx is less than infinity, this mod of y of t will also be less than infinity, which means that for a bounded input I am getting a bounded output, and that's why this system is stable. To be precise, this is Bevo stable. So this system is not memoryless, it is causal, it is linear, it is time invariant, and it is stable. So these are the 5 properties that we wanted to check for this system. Do you have any doubt in this?
Hello.
Yeah,
Can we check this Bibo stability by way of integrating, as you told, by integrating impulse response should be absolutely integrable.
you can check it by that if and only if your system is an LTI system. So yes, now when you are looking here, after proving that it is LTI, you can use that integration thing. So let us try to do that also. So if,
Yes, ma'am. Yes,
yeah,
ma'am.
let us do that also. I'll insert one slide. Okay, so
यही चीज आप सबसे ज्यादा दिक्कत हो।
here your y of t was x of t plus x of t minus 6. So what will be its impulse response?
H of t.
What do you mean by an impulse response? You have a system, and
Ma'am,
when
ratio of yt upon xt.
no, 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 no. No, no.
X of s plus
Sorry. Yeah, what will be it? Like, if you give impulse as an input, you get output as an impulse response. So here actually your x of t is equal to delta t, and your h of t is equal to y of t. Now use this relation y of t equal to x of t plus x of t minus 6 to obtain your impulse response. So just substitute x of t as delta t. So your h of t will be delta t plus delta t minus 6. Now, yeah, Bharat, please keep in mind that you can't just divide y of t by
Yes,
x of
ma'am. Yes,
t,
ma'am. Yes, ma'am.
because here we are having convolution and not multiplication. These two are totally different operations.
Yes, ma'am. Okay.
Yeah. Okay, so this is your impulse response. And what did that condition say for an LTI system? That your impulse response should be absolutely integrable. That is mod of h of t dt should be less than infinity. So let us look at this. Your impulse is having unit modulus, so it is fine. So we can drop that mod sign. So delta t plus delta t minus 6 dt. Just split it, minus infinity to infinity delta t dt plus integral minus infinity to infinity delta of t minus 6 dt. And if you observe, this will be equal to 1 and this will also be equal to 1, because
Yes, ma'am.
area
Yes,
under
ma'am.
the impulse is 1. So this is equal to 2, which is less than infinity. So this thing, this integration is less than infinity. So again, using your impulse response condition also, we are able to say that it is stable.
Yes, ma'am. Okay.
Okay. Yeah.
Yes, ma'am.
Any
Okay.
other doubt? Okay. In these examples, we'll just go with the basics for basic definitions, and we'll look at those stability, causality, and other things for LTI system also in one question. So that will be more clear in that. So let us look at this next part of this question, where my system is given as t square x of t minus 5, where this x of t is the input. So this is the question that we are looking at. So now let us look at let us first look at causality, memorylessness. So we observe this part, we can see that this is past dependency, which means that your system is not memoryless. Second thing, again we are just having past dependency, there is no future dependency, and hence the system will be causal. Now let us look at the third thing, that is linearity, and for that we will first look at its additivity. So let us look at additivity. Again for that, let's say for input x1 of t, I am having my output y1 of t, which is equal to t square x1 of t minus 5. Then for input x2 of t, my output is y2 of t, which is equal to t square x2 of t minus 5. Now if I give the input as addition of these two, that is x1 of t plus x2 of t, then my output will be t square x1 of t minus 5 plus x2 of t minus 5, which we can write as t square x1 of t minus 5 plus t square x2 of t minus 5, which is equal to y1 of t plus y2 of t. and hence this system is additive. Next thing that we need to look at is homogeneity. So let us say we gave a scaled input, that is c times x of t, and output of that will be t square into the input, that is c into x of t, which is equal to c times t square x of t. I'm sorry, this is t minus 5, which is equal to c into t square times x of t minus 5, which is equal to c times y of t. So scaled version of input is leading to a scaled version of output. The scaling factors are also same, and therefore this is homogeneous. Since it is homogeneous and additive, it is linear. Okay, so the next thing that we need to look at is time invariance. And the system that we are looking at is t of x t, which is equal to y of t, which is equal to t square x of t minus 5. So first let us shift the input. Shift input, that is we need to look at what will be the input, what will be the output if I am giving a shifted version of input. So this will be equal to, we are just shifting the input, we won't be touching this t square factor, we are just shifting the input, and therefore this will be equal to x of t minus t naught, which is shifted input, and the system again causes a shift of minus 5, and this is the output when I'm just shifting the input. Next thing, let us look at how the shifted version of output will look. That is, I need to look at what will be the value of y of t minus t naught, and let's say this is y1 of t. So now for obtaining y of t minus t naught, we need to replace every t in this y of t expression by t minus t naught. So this will be t minus t naught square x of t minus t naught minus 5, which is not equal to y1 of t, and therefore this is not time invariant, which means that it is not or in other words it is time varying system. Now let us look at the fifth thing, that is stability. Now here can we use that integral minus infinity to infinity mod of h of t dt formula? We won't be able to use it because your system, even though is linear, it is not time invariant. Therefore it is not an LTI system and we can't use that formula here. So now let us look at stability. So your y of t is equal to t square x of t minus 5, and let's say my x of t is bounded by bx, which is less than infinity. Therefore mod of y of t, that is absolute value of y of t, is equal to mod of t square into mod of x of t minus 5, which is less than or equal to mod t square bx. Now this thing, this t actually belongs to minus infinity to infinity, therefore this mod t square will belong to 0 to infinity, that is it can take infinite value, which means that my y of t is not bounded. So this is not bounded. Therefore, for any bounded input, I am not getting a bounded output, which means that it is unstable. That is, it is not Vivo's stable system. Is there any question for this particular example? Okay, let us look at the third example for this. So here my system is t of x equal to log of mod x 4t. So now let us look at this factor for memorylessness and causality. And let's say my t is equal to 1. This means that my y of 1 will be equal to log of mod of x of 4t, or let's say x of 4, and t is taking value as 1, so it will be x of 4. So this is future dependency. Also, if my t is equal to minus 1, this means that y of minus 1 will be equal to log of absolute value of x of minus 4. So this minus 4 and minus 1, this means that this is a past dependency. Since we are having a future dependency as well as a past dependency, this system is not causal and it is not memoryless. Now let us look at linearity. For that, let us look at additivity. For that again we'll take t of x1 of t will be equal to y1 of t, which is equal to log of absolute value of x1 of 4t. Similarly, t of x2 of t is equal to y2 of t, which is equal to log of mod of x2 of 4t. Now let us look at what is the value of t of x1 of t plus x2 of t. So this is equal to log of mod of x1 of 4t plus x2 of 4t, and in any sense this is not equal to y1 of t plus y2 of t. This won't lead to the expression log of mod x1 4t and log plus log mod x2 4t. So this implies that y1 of t plus y2 of t is not possible in this case, which means that it is not additive. Means that not additive. At this instant itself we can say that it is not linear, but still let us look at homogeneity. So for homogeneity, the scaled version of x of t will lead to an output which will be equal to log of mod c x of 4t, which is equal to log of mod c into mod x of 4t, and again this is not equal to c times y of t. So therefore this system is not homogeneous. and therefore this is not linear. Let us look at the fourth thing, and that is time invariance. So for that, the fourth thing that we need to look at is time invariance. And the relation that we are given is y of t is equal to log of mod x of 4t. So for that, let us first shift the input. That is, look at x of t minus t naught. And this is equal to log of mod of x of 4t minus t naught. This is only affecting your t. So it will only affect this t and nothing else. Next thing is shifting output. That is, let us look at what is y t minus t naught. So this is equal to log of mod of x of 4 times t minus t naught. That is, we need to replace all the t by t minus t naught. And again, if this is y1 of t, this shifted output is not equal to y1 of t, and therefore this system is not time invariant. Let us look at the fifth thing, and that is stability. For this, we want an output which is unbounded for any value of any bounded input. So let us take a special case where my x of t is taking value 0. For that, my y of t will be equal to log of 0, which will tend to infinity. And this is a bounded input. So there exists at least one x of t for which I am getting one x of t which is bounded, for which I am getting an unbounded output, which means that this is unstable. Any questions for this example? Okay. Let us try to understand these properties for a discrete time system. Same definitions we are going to apply, but now we will be having a discrete time system. So let us first look at this example where I am getting square of the input as my output. So for this, if you look at this part, that is x of n, we can observe that the current value of output is depending only on current input. This means that my system is memoryless and it is causal. Let us look at linearity. That is, first let us look at additivity. So for that, let's say x1 of n, if it is an input, I am having output y1 of n, which is equal to x1 of n square. Similarly, if my input is x2 of n, my output is y2 of n, and this is equal to x2 of n square. And suppose I give x1 of n plus x2 of n as input, my output will be x1 of n plus x2 of n x1 of n plus x2 of n whole square, which is again not equal to x1 of n square plus x2 of n square, because we will be getting a factor of 2 times x1 of n, x2 of n, and therefore this is not equal to y1 of n plus y2 of n, which means that this is not additive. Here only we can say it is not linear, but let us look at homogeneity. So for that, let us look at the scaled version of input, that is x of c times x of n, which is equal to c times x of n whole square, which is equal to c square into x of n square. Now we observe that we are getting a scaled version of input, scaled version of original output, that is y of n. So this is actually c square times y of n, but the scaling constant is not equal to c, and therefore this system is not homogeneous. And that's why this system is not linear. Let us look at time invariance. So for that, we are having y of n is equal to x of n square. So if I shift input, that is, let's say y1 of n is equal to t of x of n minus n naught. So these shifts are integer shifts because we are having a discrete time systems. That is, this n naught is belonging to set of integers and not any random thing. So this is equal to x of n minus n naught square. If I shift my output, that is, if I look at y of n minus n naught, then again I will get x of n minus n naught square, which is equal to y1 of n, which I obtain by shifting just the input, which means that shifted input is giving me a shifted output, and that's why this system is time invariant. Now let us look at stability. And let's say my input x of n is bounded by bx, and therefore if I look at mod of y of n, it will be equal to absolute value of x of n square, which is equal to, or let's say it is less than or equal to bx square. Again, since my bx is less than infinity, its square will also be less than infinity, and that's why this system is stable. Any questions at this point?
Hello.
Yeah.
Ma'am, can we write this xn the whole square as xn into xn?
Yes.
Yes, ma'am. Okay, ma'am, this is slight confusing because if we write x bracket n square, then the whole definition of all the things will change.
1 minute.
Like system
I'm
will
not
not
getting your
be.
question. Your system is like this: x of n whole square
Ah, yes,
and
ma'am. Yes,
not
ma'am.
x of n square.
Ah, yes, ma'am. Because
This
if
is
we write
not the
x of,
case.
no, ma'am. If this would be the case, then all the definitions of causality will change because
Everything
that
will
will.
change. Everything will
Ah, yes,
change.
ma'am.
So we are looking at this and not this.
Ah, yes, ma'am. Yes, ma'am. Okay, okay.
Mhm. Okay. I hope this point is clear. Like, please don't get confused in this. If I'm doing anything with this n, it will always be inside this bracket. It will be like this and not like this. If I am trying to play with this n, that is independent variable, it will always be inside the bracket. So I'll mention this because if you get these notes, it will be easy for you to refer back. Okay, let us look at the second part of this question. So this is the system that is given to us. Again, first we'll look at memorylessness and causality, and if we look at this point, again it is only depending on current value of input, which means that it is memoryless and it is causal. Next, let us look at linearity. So for that, we'll first look at additivity. Again, we'll use the similar definitions, that is x1 of n will give me y1 of n, which is equal to absolute value of x1 of n, then x2 of n will give me y2 of n, which is equal to absolute value of x2 of n. Now if I look at x1 of n plus x2 of n, I will get absolute value of x1 of n plus x2 of n, which will be less than or equal to absolute value of x of n plus absolute value of x2 of n, which is equal to y1 of n plus y2 of n. So basically this thing is less than or equal to summation of y1 of n plus y2 of n, and it is not equal to. It will be equal in very special cases and not for any general case, and that's why this is not additive. Next thing that we'll look at is homogeneity. And this is if my input is scaled by a factor of c, its output will be c times absolute value of c times x of n, and this is equal to mod of c into mod of x of n. Now one should note that this absolute value of c may not be equal to c if it is complex or if it is a negative value, and therefore this is not equal to c times y of n, and hence this is not homogeneous. And since it is not additive and it is not homogeneous, this is not linear. So let us look at the fourth one, that is time invariance. And for that we are having y of n equal to absolute value of x of n. So let us first shift input. So for that, the shifted input's output will be equal to absolute value of x of n minus n naught. Let's say this is y1 of n. And now if I shift output, that is if I look at y of n minus n naught, then it will be again equal to absolute value of x of n minus n naught, and this is equal to y1 of n. Since shifted input is leading to a shifted output with same shift, this is a time invariant system. The fifth one that we need to look at is stability. So let's say this x of n is bounded by a factor of bx, and we know that this itself is equal to y of n, which implies that my y of n is also bounded by bx. Also absolute value of mod of y of n, that is output, will also be bounded by this bx, which means that for any bounded input I'll be getting a bounded output, and hence it is Bose stable system. Any questions for this example? Okay. So let us look at the final example of this kind, and for that my input output relation is given by this form. Again, if I look at this factor here, that is which is based on input, it is again based on current instance input, that is current input, which means that first of all it is memoryless, and secondly it is causal. Now let us look at additivity. So suppose my y1 of n is equal to t times x1 of n. This will be equal to 2 times x1 of n plus 5 square. Similarly, let's say my y2 of n is output for input x2 of n, which is equal to 2 times x2 of n plus 5 square. So if I am having addition of these two inputs, that is x1 of n plus x2 of n as my input, then I'll be getting 2 times x1 of n plus x2 of n plus 5 whole square. And if we simplify this will not at all be equal to y1 of n plus y2 of n, which means that this system is not additive. Next we'll look at homogeneity. Link of this class, so you might have got through your email, I think. Yes. 1 minute, I'll share. Oh, the recorded sessions are available on YouTube. You can just search for my YouTube channel by name Shivani Dhok, and you will find even the last lecture is also uploaded on YouTube. It will be uploaded on the same day by night, so you can find it on my YouTube channel. Let us look at homogeneity. Okay, so for that, let us look at C times x of n, that is the scaled version of input. So this will be equal to 2 times C of x of n plus 5 square, and again this is not equal to scaled version of output, that is C of y of n, which means that this is not homogeneous. And since it is neither homogeneous nor additive, this is not linear. Let us look at time invariance. So for that, first let us shift the input, and the input output relation that we have is y of n is equal to output for input x of n, which is equal to 2 times x of n plus 5 square. So if I shift the input, that is if I look at the output for x of n minus n naught, this will be equal to 2 times 2 times x of n minus n naught plus 5 square. Secondly, if I shift output, then y of n minus n naught will again be equal to 2 times x of n minus n naught plus 5 square, and if I name this as y1 of n, then this will be equal to y1 of n. Since shifted input is giving me a shifted output with same shift, this is time invariant. The fifth one that we need to look at is stability, and for this, let's say my input x of n is bounded by some constant bx. So now let us look at absolute value of y of n, which is equal to absolute value of 2 times x of n plus 5 square, which is equal to, you can just interchange absolute value and square, since it is a single value, so we can just have it. No, let's not do that. Let's simply solve this as 4x of n whole square plus 20x of n plus 25, which is less than or equal to 4 times absolute value of x of n square plus 20 times absolute value of x of n plus 25, and this is using triangular inequality. And this is again less than or equal to 4 times bx square plus 20 times bx plus 25. Since my bx is less than infinity, this entire expression will also be less than infinity, and therefore my output is also bounded. Therefore, for any bounded input, I am getting a bounded output, and hence this is a Bibo stable system. Yeah. Any doubts in this question?
Hello, ma'am.
Yeah.
Ma'am, here we are dealing with the discrete time signals. So here we can say that if for a system to be Bibo stable, as impulse response should be absolutely summable because we can't integrate the discrete time signals.
Exactly.
Yes, ma'am. Yes,
Yes,
ma'am.
yes,
That's the.
yes. But it should be LTI system.
Yes,
This
ma'am.
is not
Okay.
an LTI system. This is
Ji,
not
ma'am. Okay.
linear. So if your system is LTI, you can say that if your impulse response is absolutely summable, then your system is stable.
Yes, ma'am. Okay. Okay.
Okay, so if there are no further questions, we'll go to the next question. So what it says is, based on impulse response of the systems, comment on the causality and stability of the following systems. So let us look at the first one. So it says that your h of t is equal to e power minus 2t u of t. But this u of t is your unit step signal. How does this signal look? So it is a decaying exponential. So this is my time axis like this, and this is my h of t, and the signal e power minus 2t at t equal to 0 takes the value as 1, and then it decays like this and goes to 0 as my t tends to infinity. And for all other values, that is for all the t less than 0, it will be 0. So we observe here that my h of t is equal to 0 for all t which are less than 0, which means that the system is causal. Now let us look at the stability. For stability, what do we need to look at? We need to see whether this is absolutely integrable. So this is equal to minus infinity to infinity absolute value of e power minus 2t ut dt. Now we observe here from minus infinity to 0, this is 0, this signal is 0, so we can conveniently change the limits from 0 to infinity. Again, this h of t is always positive, so we can ignore that absolute sign. So this is equal to e power minus 2t dt, which is equal to e power minus 2t from 0 to infinity, and this is equal to 1 by 2, which is less than infinity. And since it is absolutely integrable, this is stable. Any questions at this point? Okay, let us look at the second part. That is, I am having h of t is equal to u of t plus 2. So this signal looks something like this. Your u of t starts from t equal to 0, but this is a shifted version. So it will start from minus 2. So at minus 2, it will take a value of 1, and then it will extend till infinity. This is my t axis, and this is my h of t. So we observe that for t equal to minus 2 to 0, this signal is not equal to 0, which means that it is not causal, or rather specifically it is non-causal system, because you are having some values of t for which are greater than 0, for which it is non-zero, therefore it is not anti-causal, it is non-causal system. Now let us look at stability. So for that, again, minus infinity to infinity absolute value of h of t dt. So this will be starting from minus 2 to infinity, because it is non-zero from minus 2 to infinity, and h of t takes value as 1 in that range. So this is 1 dt, which is equal to t from minus 2 to infinity, and this tends to infinity, which means that not absolutely this is not absolutely integrable, which means that it is unstable. Is it okay? Any questions at this point? Okay. So let us look at the third one. So it is h of t equal to e power 2t u of t. So this is not a decaying exponential, rather it increases with time. At t equal to 0, it is 1, and then it increases like this, and sorry, it will go like this. It will settle to infinity at t equal to infinity, and before this it is equal to 0. So again we observe that for all the values of t, so we observe here because of this u of t, for all the values of t which are less than 0, my h of t is equal to 0, which means that it is causal system. Now if I look at this integral from minus infinity to infinity, absolute value of h of t dt, we observe that it will again run from 0 to infinity due to this u of t, and again this is a positive value, so it is e power 2t dt, which is equal to e power 2t by 2 from 0 to infinity, which tends to infinity, which means that this is unstable system. Now let us look at the final part of this question, and it is h of t is equal to e power 2t u of minus t. So now this is the flipped version, like actually it looks something like this. At t equal to 0, it takes value 1, and then it decays towards minus infinity. So this is my h of t. So now if we observe here, it is non-zero in this region. That is, for all t which are greater than 0, my h of t is equal to 0, which implies that this is anti-causal system. And now let us look if it is stable. So we'll look at minus infinity to infinity, absolute value of h of t dt. Now this is ranging from minus infinity to 0, and in that it takes the value of e power 2t dt. So this is equal to e power 2t by 2 from minus infinity to 0, and this is equal to 1 by 2, which is less than infinity, which means that this is stable. Any questions at this point? If not, let us look at the next question. So here I am having a system whose input output relationship is given as y of t equal to x of t plus 3x of t minus t naught minus 2 times y of t minus t naught. Now this y of t minus t naught, that is some past value of output, is fed back as an input to the system, and therefore this is an example of feedback system. So we need to look at this system and check whether this kind of system is an LTI system or not. So first we'll look at its linearity. So first we'll look at linearity, and in that first we'll look at additivity. So for that let's say y1 of t is equal to t of x1 of t, which is equal to y1 of t plus y1 of t is equal to 3 times x1 of t minus t naught plus x1 of t minus 2 times y1 of t minus t naught. Then let's say y2 of t is output when my input is x2 of t. So this is equal to 3 times x2 of t minus t naught plus 3 times x2 of t minus 2 times y2 of t minus t naught. And let's say y3 of t is equal to the output of system when my input is x1 of t plus x2 of t, and for that it will be equal to x1 of t plus x2 of t plus 3 times x1 of t minus t naught plus x2 of t minus t naught plus minus 2 times y3 of t minus t naught. Now let us add these two, that is y1 of t plus y2 of t. Let us look at this. There is y1 of t plus y2 of t is equal to x1 of t plus x2 of t plus 3 times x1 of t minus t naught plus 3 times x2 of t minus t naught minus 2 times y1 of t minus t naught plus y2 of t minus t naught. And if we compare this equation A and equation B, we observe that your y3 of t is equal to y1 of t plus y2 of t, which implies that this is an additive system. So this is additive. Now next let us look at homogeneity. So let us say that for y1 of t is my output when I am scaling the input. So this is equal to c times x of t plus 3 into c times x of t minus t naught minus 2 times y1 of t minus t. Now let us look at what is this c times y of t. So that will be equal to c times x of t plus c times 3 into x of t minus t naught minus c times 2 times y of t minus t naught. So again, if I look at these two equations and compare them, I can say that y1 of t is equal to c times y of t, which means that this is a homogeneous system. Since it is homogeneous and it is additive, it is linear. Now let us look at the second thing, that is time invariance. And for that, first we'll shift the input, and let's say first we'll shift the input, that is, let's say my y1 of t is output when I'm supplying shifted input. It is x of t minus t1. So this is equal to x of t minus t1 plus 3 times x of t minus t1 minus t naught minus 2 times y1 of t minus t naught. Now second, let us shift output. That is, we'll look at what is y of t minus t naught. So this is equal to y of t minus t1. So this is equal to x of t minus t1 plus 3 times x of t minus t1 minus t naught minus 2 times y of t minus t naught minus t1. So again, if I compare these two expressions, I can see that my y1 of t is equal to y of t minus t1. That is, when my input is getting shifted, my output is also getting shifted by same shifting factor, and therefore it is time invariant. And since it is linear as well as it is time invariant, it is an LTI system. Therefore, if I'm having a feedback system which is something like this, it will be an LTI system. Any questions at this point?
Hello.
Yeah.
Excuse me. In first equation, when we shift the input by
Hello? I'm not able to hear you.
hello,
Yeah.
in first equation, when we shift the input,
Hmm.
the output was not the last term, that is minus two y of t minus t0.
Hmm.
But in second, when we shift the output, we are getting minus 2 of y of t minus t0 minus t1.
Yes. My y
But
of
this,
t, like when I'm shifting my output, I'll replace all the t that are in this equation by t minus t1.
but when we are shifting the only input, the two equations are not same. No?
No, 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 no. No,
Last
no,
term.
wait. I am assuming that this y1 of t is an input, is the output of the system when I'm shifting the input. And then I'm analyzing, if I shift the entire output, then what is the output that I am getting? What is the equation that I am getting? And after that, I am comparing these two equations term by term. And from that, I am concluding that this y1 of t is equal to y of t minus t1. You can see here it is y1 of t, and here it is y1 of t minus t naught. Here I am having y of t minus t1, and here this y of t minus t1 is shifted by t naught. So if I say
Okay.
that this is t dash, this y of t dash will be equal to y of t dash minus t naught. And if I compare these two, these are actually the same terms that I am getting. So by comparison, I am saying that y1 of t is equal to y of t minus t1.
Okay. In that case, the term should not be same, but the it should be shifted by same amount only.
Yes, I am just naming this as some variable for my convenience and then comparing these two equations. Like I don't know what is the output when I'm shifting the input. So for that I should have some variable y1 of t, and then I'm trying to analyze what is happening when I'm shifting directly the output, and then analyze if these two are comparable or if these two lead to same things. Is it okay? Okay, let us look at the next uh, question, and that is prove the distributive property of convolution. So what is this distributive property? So if I am having a signal x of t and I am convolving it with addition of two functions, something like this, that is convolving it with x1 of t plus h2 of t, then this is equal to x of t convolved with h1 of t plus x of t convolved with h2 of t, and we need to prove this. So for that, let us consider this LHS, and by definition of convolution this will be equal to minus infinity to infinity x of tau, and this entire thing is my h of t. So we need here h of t minus tau, so that will be equal to h1 of t minus tau plus h2 of t minus tau d tau. So this will, we can separate out these integrations, something like this, minus infinity to infinity x of tau h1 of t minus tau d tau plus integral from minus infinity to infinity x of tau h2 of t minus tau d tau. Again, by definition of convolution, the first integral is x of t convolved with h1 of t plus the second integration, that is x of t convolved with h2 of t, and this is the proof for your distributive property of convolution. Let us look at the next question. So here we are having two subparts and we need to find the convolution of x of t, any arbitrary input with impulse which is located at t minus t naught. So my impulse response is basically something like this. This is 0 and I am having an impulse which is located at t naught. So we need to find convolution of x of t with del of t minus t naught. So this is equal to integral from minus infinity to infinity. Okay, for convenience, let us use commutative property of this convolution. So this is equal to del of t minus t naught convolved with x of t, and this can be written as minus infinity to infinity del of tau minus t naught. So this is del of tau minus t naught into x of tau d tau. Now here I can use the shifting property and I can write this as integral from minus infinity to infinity del of t minus t naught x of, sorry I made some mistake here, this is convolution, so it is t minus tau d tau. So after doing this, yeah, integration of delta tau minus t naught into x of t minus t naught, the convolution is with respect to variable t. So here, by shifting property, this tau will take the value of t naught where this impulse is located, d tau. Now this is constant, we can take it outside, and integration of any impulse from minus infinity to infinity is equal to 1. So therefore this is equal to t minus t naught. Therefore, if I convolve any input, any x of t with shifted delta t, that is shifted impulse, my input gets shifted to that point. That is, if I am convolving x of t with delta t minus t naught, the output will be x of t minus t naught. Now using this, let us try to solve this second part. So what I am having in second part is x of t being convolved with delta, this is t plus 1.5 minus delta t minus 1.5. We can use distributive property here. So here it will be x of t convolved with delta t plus 1.5 minus x of t convolved with delta t minus 1.5. So here we used distributive property. So this is equal to, using this property which has been derived in equation 1. So using equation 1, this is equal to x of t plus 1.5 minus x of t minus 1.5, and this is equal to, using this equation given here, 3 power minus t plus 1.5 into u of t plus 1.5 minus e 3 to the power minus t minus 1.5 into u of t minus 1.5. So this is the answer of second part. Any questions till this point? Okay. Now let us look at this seventh question. What is given? We are given one signal x of t which is equal to e power t u of minus t. So the signal looks something like this: e power minus t u of t. So this is x of t which is e power t u of minus t, and I need to convolve this signal with x of minus t. Okay, so let's say this is equal to y of t. So I need to find y of t which is equal to x of t convolved with x of minus t. So let us use the definition first, that is minus infinity to infinity x of tau into x of minus of t minus tau d tau. So this is my h of t. If I say, then this part is h of t minus tau. Okay, now let us substitute these things here. So minus infinity, so this is equal to integral from minus infinity to infinity. X of tau is e power tau u of minus tau, and x of minus t minus tau is equal to e power minus t minus tau into u of t minus tau d tau. Okay, now let us simplify these. Let us look at this term and this term. So if I combine these two terms, this e power tau and e power minus t minus tau gets converted to e power 2 tau, that is minus infinity to infinity e power 2 tau, and remaining is e power minus t, so that we can just take outside into u of minus tau into u of t minus tau d tau. Now let us focus on these two parts and try to draw them. So first thing that we need to look at is u of minus tau. So this is my u of minus tau. And I will be shifting this u of t minus tau is flip u of t and then shift it. So if my t is less than 0, that is if my t is somewhere here, this will be u of t minus tau when my t is less than 0. Now in this case, this region is the region of overlap, and that's why this integral for case 1, that is when my t is less than 0, this integral will be equal to minus infinity to t e power 2 tau into e power minus t d tau. And this, after solving, we obtain as e power minus t e power 2 tau by 2 from minus infinity to t, and after simplifying we obtain this as e power t by 2. Second case is when my t is greater than or equal to 0. So in this situation I am having it something like this. My t is greater than 0, and now this is the region of overlap, that is from minus infinity to 0. Therefore this integral now becomes y of t is equal to e power minus t from minus infinity to 0 e power 2 tau d tau, and this is equal to e power minus t from, this integral is e power 2 tau upon 2 from minus infinity to 0, and this is equal to e power minus t by 2. So basically we are having two cases. So my output y of t is based on two cases. So for the first case my output is e power t by 2 when my t is less than 0, and it is equal to e power minus t by 2 when my t is greater than or equal to 0. So this is the answer for the convolution. Are there any doubts for this question? Okay, let us look at the next question, and it is again what we are given is we are having a system. We are having a system whose impulse response is given as u of t, and at input we are having x of t, and this is an LTI system, and we need to find what is the output y of t. So again this y of t will be equal to convolution from minus infinity to infinity x of tau e power x of tau h of t minus tau d tau. Now let us first draw how this x of tau will look as. So let's say this is my tau axis, and my first I'll draw what is x of tau. So again it is a decaying exponential, that is e power minus tau u tau. So it is something like this, and it is 0 till 0. And next thing that we need to look at is my impulse response, but first thing that we need to do with my impulse response is flip it. So if my impulse response is u of t, its flipped version is u of minus t, which will be looking something like this, and its amplitude is 1, and this is u of minus tau. and now I need to shift this u of minus tau from minus infinity to infinity. That is, I need to shift this, I need to shift this by t, and t will be varying from minus infinity to infinity. So let us say in the first case my t is somewhere here, that is my t is less than 0. So the case 1 is my t is less than 0. So my impulse response will be something like this. The flipped and shifted impulse response will look something like this, and this is u of t minus tau. So if I observe x of tau into u of t minus tau when my t is less than 0, the product element, point by point product of these two signals, this one and this one, will be equal to 0, and therefore this integral for the case 1 when my t is less than 0 will be equal to 0. Now suppose now my t is greater than 0, that is somewhere here. It is something like this. So now if I observe these two equations, that is, this is the case when my t is greater than 0, this is u of t minus tau. And if I look at this one and this one, this area, this shaded region is the region of overlap. And therefore for my case 2, my convolution output y of t will be equal to the only region where these u of t minus tau and x of tau overlap, that will be 0 to t. My x of tau takes the value as e power minus tau in this region, and my u of t takes the value of 1 in this region, d tau, and this integral is equal to from 0 to t, and this reduces to 1 minus e power minus t. So again in this question, my y of t takes two values. One is 0 if my t is less than 0. It is equal to 1 minus e power minus t when my t is greater than or equal to 0. Any doubt in this question? Okay, let us look at this question. This question, if I remember right, it was in GATE 2019 or 2020. I don't remember the exact year, but this was in GATE, and it is actually based on discrete time systems impulse response and input. So actually, let us first look at one simple. Let us first look at how the convolution will look for a discrete time signal system. So if my impulse response is h of n, and if my input, so this is impulse response, and if x of n is my input, then output of the system, that is, I'm having a system with impulse response h of n, its input is x of n, and its output is y of n. So its output y of n is given as a summation with running variable as k from minus infinity to infinity, x of k, h of n minus k. And this can also be written as x of n convolved with h of n. So this is convolution for discrete time. This is discrete time convolution. Okay. Now any discrete time signal or system can be represented using a sequence, that is, if my h of n is something like this, let's say at 0 it takes value 0, 1, and at 1 again it takes value as 1. So this h of n can be simply represented as 1 comma 1, and to indicate the position of 0 we can write as something like this. So this is n, and for other values of n it is 0. So in this case we can simply write it as a sequence something like this, h of n as a sequence 1 comma 1 with starting from 1 at 0, that is this index 0, h of 0 is indicated with an up arrow just below its position. Similarly, if I am having an x of n something like this, let's say it is 3, 2 and 1, then x of n can also be written as 3, 2, 1, and again 0th index is indicated by this point 0. Now let us look at how this x of n convolved with h of n will look. So for that first we'll need to flip this, that is we'll first need to find what is h of k. So this will be equal to 1 comma 1, but now it will be something like this, that is we are just flipping this h of n, whatever was at 1 will be now be available at -1, and 0 thing will remain like this, and rest will be equal to 0. So this is my h of minus k, and then we need to shift it one by one. So this we can easily do in some tabular form, like if I am having this x of n, and suppose this is like this 3, 2, 1, this is my 0th index, and let us look at what is this h of minus k plus n. So if we observe that if we look at n equal to 0, it is something like this. Now if I consider n, this is at n equal to 0. Now if I look at this and observe, if we look at this and observe this shifts, that is for all the negative shifts my h of n there won't be any overlap, and therefore for all the values of n less than 0 its convolution will lead to 0. But if I'm having n equal to 0, I'll have one overlap here, so this will be basically my h of minus k. Then if I'm having h of 1 minus k, then I'm shifting it by 1, so it will be something like this, so and so on. That is for, we can just use a tabular form and shift it one by one. Let us try to do it in a very on new slide. So I'm having x of n 3, 2, 1, and I'm having h of minus k. This is my 0th index, that is it is 1, 1, this is my 0th index, and first thing that I'll find is y of 0, which is x of k multiplied by h of n minus k. Since there is only one value that is being overlapped, the summation will reduce to only one value here, that is equal to h of minus k, which is equal to 3. If I do h of 1 minus k, I'll shift these things by 1 point here. Now this is at 0, so my y of 1 will be equal to, this is x of 1 Here my k value is 0. So this is x of 1 into this factor, that is h of 1 minus 1 plus x of 1, x of, so this is actually x of 0 into h of 1 minus 0 plus x of 1 into h of 1 minus 1. So this is equal to 3 plus 2, which is equal to 5. Similarly, if I shift it one more time, again I am having overlap of two factors, that is, then my y of 2 will be 2 into 1. So this is h of 2 minus k, the rest all are 0. So now I am having overlap of these two numbers, this and this, this and this. So it is 2 into 1 plus 1 into 1, that is 2 plus 1, that is equal to 3. And h of 3 minus k, if I consider, then it will be something like this. That is, there will be again only one overlap of 1 and 1. So my y of 3 will be again 1. Now if we observe here, after n greater than or equal to 4, that is after n equal to 4, there won't be any overlap with x of k, and therefore for y of n, for n greater than or equal to 4, this y of n will be equal to 0. Similarly, for n less than 0, it will be equal to 0. Now let us try to look at the length of these two sequences. What was my x of k? Or rather x of n? My x of n was a 2 length sequence. So its length was 2. Let's say Lx was 2. If I look at my h of n, then it was 3, 2, 1. That is 3, which was L of y, that is length of y. And my y of n is equal to 3, 5, 3, 1. So this is 3 at 0, 5, 3, 1. That is, this is L of h. That is L of y is equal to 4. And if I try to formulate the relation between these, my L of y is equal to L of x plus L of h, which is equal to, L of x plus L of h minus 1, which is equal to 2 plus 3 minus 1, that is equal to 4. So this relation holds every time. Another thing that we can look here is, this is my 0th index, this is my first index, this is 0, 1, 2, this is 0, 1, 2, 3. The starting index of the sequence is 0 plus 0, that is starting index addition, that is 0 plus 0, 0, and the last overlapping index is 1 plus 2, that is addition of last two indices, that is 1 plus 2, which is equal to 3. So these things help you if you solve some questions which are in competitive exams, and also help you to check whether whatever answer you are getting are correct or not. I hope this explanation is fine with you. If this is okay, we'll move on with that question that we want to solve. Okay, so what we are given here, we are given here with an impulse response h of n equal to 1, 1, 1, 1, which is starting from 0, and here we observe that LH is equal to 4. Now we are given some information about y of n. So what we are given? We are given y of 0 as 1, y of 3 as 10, y 5. So yeah, y of 5 is equal to 7, y of 2 minus 2 times y of 1 is equal to 0. So we are given a sequence y of n is equal to, at 0 it is taking value as 1, at 2 we don't know what is, at 1 let's say value is y1, then at 2 y of 2 minus 2 times y of 1 is equal to 0, so this is 2 times y of 1. Then y of 3 takes the value as 10. Y of 4 we don't have any information, so let's keep it as it is. And y of 5 we are given as 7. And y of 6 again we don't have any information. Also we are given that this y of n is 0 for n less than 0 and for n greater than 6. So basically what information it is giving us is that this this L of y is actually equal to 7. Now if we use this equation L of y equal to Lx plus Lh minus 1, that is, if I look at this, L of y is equal to Lx plus Lh minus 1, then we can find what is the length of input. So I have 7 is equal to Lx plus my impulse response is of length 4 minus 1, which means that my Lx, that is input, is of length 7 minus 3, which is equal to 4. So basically my input x of n is a 4 length sequence. Again, this input is starting from 0, my output is also starting from 0. I'm sorry, my impulse response is starting from 0, my output is starting from 0. So if I add those index, it is 0, which means that my input will also start from 0, then x of 1, x of 2 and x of 3. So I need to find these 4 values of input. So now using this sequence and this sequence, let us try to find out. So we know the relation, which is convolution. So y of n is equal to n equal, so k equal to minus infinity to infinity x of k h of n minus k. So now let us find the equation for y of 0 from this given first equation, convolution equation. So my y of 0 is equal to summation x of k h of minus k. Now if I vary my k from minus infinity to infinity, my h of k will be non-zero. My h of k will be non-zero if I take a value of k greater than or equal to 1, because for that this will become 0. That is, if I take k greater than or equal to 0, it will be something like this: x of k into h of minus k, where this minus k is some negative quantity, and we observe that this h of n is 0 for all the values of k less than 0 or n less than 0. Similarly, if I vary k from minus infinity to minus 1, then this x of k will be 0, because x of n is 0 for all the values of n which are less than 0. Therefore, the only value of k for which it will survive is 0. So I am having this as x of 0 into h of 0. Now I have the values of y of 0 as 1 and h of 0 as, h of 0 as 1, and this y of 0 is equal to 1, which means that my x of 0 is equal to 1. Next thing that we can do is we can try to use this equation here, that is y of 3, and try to obtain its value, or we can use y of 5. Let's use y of 5 first. So if we look at y of 5, it is equal to summation of k running from minus infinity to infinity, x of k, h of n minus k, and this is equal to x of 2, h of 5 minus 2 plus x of 3, h of 5 minus 3. And if we solve it further, we will observe that we will get all the other terms will get to 0. Yeah. And if we solve it further, then we can obtain this something like this. So my y of 5, if you solve it properly, it will be equal to x of, I'm sorry, I'm making some mistakes. Wait a minute. No, yeah, it's okay. So it is x of 2 plus x of 3, and we have the value of y of 5 as 7. So let us keep this equation as it is, and now let us try to find what is y of 3, because we have its value here. So if you solve this, you will obtain this as x of 0 plus x of 1 plus x of 2 plus x of 3. I request you to just solve it by yourself once, because due to time restriction I'm just providing the solution of it, and this is equal to 10. And if I subtract this equation 2 and this equation 3, I obtain x of 0 plus x of 1 is equal to 3. So I am subtracting 3 and 2, and we have obtained x of 0 as 1, therefore x of 1 is equal to 2. Okay, now we have another relation, that is y of 2 is equal to 2 times y of 1, and we found that this y of 1 this y of 1 we don't know, we want to find the value of this. We have this relation, and if we find the value of this y of 1, then actually it is equal to x of 0 into h of 1 plus x of 1 into h of 0, that is equal to 2 times x of 0 plus x of 1, and this is equal to 2 times, we have obtained this value as x of 1 plus x of 0 as 3. So this is equal to 2 into 3, which is equal to 6. Now this is equal to y of 2, and this y of 2 is equal to x of 2 into h of 0 plus x of 1 into h of 1 plus x of 0 into h of 2, which is equal to x of 2 plus, again h of 1 and h of 2 are 1, therefore x of 1 plus x of 0, which is equal to 3, which is equal to 6. Therefore x of 2 is equal to 3. So now we have the value of x of 0, x of 1 and x of 2, and we can substitute all of these in this equation 3. Therefore, from equation 3 we can substitute x of 0 as 1, x of 2 as 2, x of 3 as 3 plus x of 3. So this is x of 0, x of 1, x of 2, which is equal to, so this is given as equal to 10. Therefore my x of 3 is equal to 4. Therefore my sequence x of n is 1, 2, 3, 4. Any questions in this question? Any doubts in this question? Okay, let us look at this final question for today, and in this we need to look, we are given this x of t. So we know that this is the eigenfunction of an LTI system, and with its impulse response is given something like this, and we need to find the transform. In the example which was taken, or in the course lecture which was taken, we were given that x of t was given as e power alpha t, and this was your eigenfunction. And your transform h of alpha was obtained as integration from minus infinity to infinity e power minus alpha tau h of tau d tau. So this was what was obtained in the lecture that was given. This was known as your eigenfunction, which was exponential, and this is your transform, and we need to find what is the value of your transform for given impulse response. So let us substitute it. So minus infinity to infinity. Here your alpha is j omega t. Sorry, your alpha is j omega, where this j is square root of minus 1. So this is e power minus j omega tau, and your h of tau is e power minus tau u tau t tau. Now this unit step will just change your integration limits from 0 to infinity. E power minus j omega tau into e power minus tau d tau. This we can write as e power minus tau 1 plus j omega integration from 0 to infinity d tau. This is equal to e power minus tau 1 plus j omega upon minus of 1 plus j omega from 0 to infinity. This is equal to 1 upon 1 plus j omega. So this is the value of h of j omega, which is your transform. So this was the last question that I planned to cover today. If you have any doubts, please let me know. If you don't have any doubts, then you're free to leave the meeting.
Hello, ma'am. Ma'am, these lectures are also available on NPTEL portal of course page also.
I have to check if they have uploaded the YouTube links. Actually, we were told that they will upload the YouTube links so that you can refer it back. But I assure you that all these lectures will be uploaded on YouTube on my channel. You can just search for Shivani Dhok That is my
Yes,
mail.
ma'am. Yes, ma'am.
You will find all week's lectures. Like I'll upload it by the end of the day.
Yes, ma'am. Okay, okay. Thank you.
Yeah. Okay. If there are no further questions, let's stop for today. Thank you for the meeting.